So we were talking about convex optimization problems, and and we saw that the we have to minimize a function f naught of x, and this function is convex, subject to inequality constraints, and equality constraints such that first the objective function is convex, that is f naught, in equality constraints are convex, and HIs are affine. And the domain of the domain is intersection of all the objective function and inequality function, so the domain of them. Then we also mentioned that local and global optimal are same, and this domain is a convex set. We can see this from intersections of convex domains of convex functions. Then we talked about optimality criterion for differentiable f naught. So we are saying that f naught, given it is differentiable, and we take, so f naught is convex, so we know 2 points belonging to domain of f naught, then f naught of y is greater than or equal to f naught of x plus del of f naught of x into y minus x. This is from convex, f naught is convex, and we denote x by x the feasible set, that is x, such that all the fi's are less than or equal to 0 from I equal to 1 to m, and hi's equal to 0 from I equal to 1 to p. And then we say that x is optimal if and only if x belongs to x, and so and y minus x greater than equal to 0 for all y belonging to x. So given we have x and y should be part of the feasible set, then if this condition is followed, so x is optimal. Okay, we will now see the proof of the optimality criterion. So this is an if and only if condition. So proof. So we first suppose that x belongs to x, capital X, and this condition is true, and we want to arrive at x is optimal point. So we say x belongs to x and satisfies satisfies 1. Then we choose a y such that it belongs to capital X, and by this equation we see that f naught of x, f naught of y is greater than equal to f naught of x plus del of f naught of x into y minus x. So we just said that it satisfies equation 1, so this is positive value. So this means this is greater than f naught of x. So we say that f naught of y is greater than equal to f naught of x. And this proves that x is optimal. And this proves in one direction. And next we say that we first say that x is optimal, and x does not satisfies 1. So we say that it does not satisfy this condition, and we will arrive at this condition by contradiction. So it means that if it does not satisfy, it means that f naught of del of f naught of x into y minus x is lesser than 0 for all y belonging to x. For some, not all, because even if it does not holds for some of the y's, then this condition is not fulfilled for some y belongs to x. Okay, so and then we take z of t. So z is a point in the line segment joining y and x, and it is a parameterized point with a parameter t, where t varies between 0 and 1. So since domain of f naught is a feasible set, f naught is a convex set, so uh, the line joining y and x, all the points in that line will be the part of the feasible set. So z dot t is feasible, and now we take a derivative over with respect to t of f naught of z of t at t equal to 0, and this is equals to del of f naught of x and which we have seen, which we have said is lesser than 0. So this means for any small value of t, f naught of z of t is lesser than f naught of x. So this will say that x is not optimal, because if f is x is optimal, this condition we could not have arrived. So this contradicts our assumption that uh, this is lesser than 0. So hence, if x is optimal and x belongs to capital X, then this condition holds. For unconstrained problems, we see that this condition leads us to f naught of del of f naught of x is equal to 0, and this is kind of explanatory, like so. It's like this. Uh, the optimal point will have a slope of 0 if it's unconstrained, so it will have the entire of the domain of the function, convex function, and it will be optimal at the point where del of f naught of x will be equal to 0. We can also arrive at this expression from our previous condition. So for that, let us take a point y equals to x minus t del of. So this is a point very close to x. So t is a parameter belongs to R. So for and we are saying that t is small and positive. Positive. This is our consideration. So so if we put this in this equation, so we get of x t y minus x equals to del of f naught of x t x minus t minus x. And which we know, uh, so this is positive and this is positive, and there is a negative sign, so this can on this situation, and we know this is small positive, so we have taken this as a positive value, and this will always be positive. This uh, inequality can only be true if we can see that this is equal to 0. If it is equal to 0, then this will turn to equality that is equal to 0. So for unconstrained problems, the condition is f del of f naught of x should be equal to 0. Okay, and now we will see another such thing, problems with equality constraints only. So here we have to minimize f naught of x subjected to ax equal to b, and there is no inequality constraints. So the optimal condition on x would be, so we know we are using the differentiable criterion, and here the y must hold this criteria, ay equals to b, and since x is feasible, y should be feasible, and of the form y should be equals to x plus v, where v belongs to null of a. Why? Because a y equals to b means a x plus v equals to b, means ax plus av equals to b. So this can only be true if av equals to 0. That means v belongs to null of a. Okay, so we replace this value here, and we come up with v greater than equal to 0 for all v belongs to null of a. And here is a claim: if a linear function is non-negative, on a subspace, then it must be 0 on the subspace. Proof of the claim is, let's suppose f of x is f of x greater than equal to 0 is the linear function on a subspace S and x belongs to S. So by the property of the subspace, f of minus x is also non-negative on the subspace, and by the linearity property of the function, this is also greater than equal to 0. So this can only be true if f of x is equal to 0. So this means del v should be equal to 0. From here we reached here. So so this means del of f naught of x is orthogonal to v, perpendicular to v. And v belongs to null of a, means del of f naught of x perpendicular to null of a. Also if anything is perpendicular to null of a, it belongs to range of a transpose. So it means f naught del of f naught of x belongs to range of a transpose. That is, there exist a v belongs to Rp from here, and this we see that v also belongs to Rp. We didn't mention it. Okay, so this means that there exists a del of f naught of x plus a transpose v equal to 0. Now we see minimizing over non-negative orthant. So non-negative orthant is all the elements in the vector, all the xi's I equal to 1 to p, all the xi's are greater than equal to 0. So then it is called a non-negative example is this is an orthant. Okay, so minimizing f0 f naught of x subject to non-negative orthant. So again we use the optimality condition, that is y minus x greater than equal to 0 for all y also a non-negative orthant. So del of f naught of x, y is a linear function in y, and we can see that it is unbounded below on y equal to y um, so I mean del of f naught of x, y is a linear function in y, and we can see that it is unbounded in y, in the non-negative orthant of y, unless this holds. So we can reduce this to the condition this to be also be, and so this is this we are saying is and also x. So this can only be possible if, and this is a negative sign is there, so this can only be possible if uh, del of f naught of x is actually equal to 0, and this is summation of, we can means expand this as a summation of I equals to 1 to n, so which means that sum of all these non-negative numbers must be equal to 0, and which means that all of them sum of all the non-negative numbers is equal to 0. It means that all of them must be equal to 0, all the xi's, all these products must be equal to 0 for I equals to 1 to n. So the optimality condition is finally reduced to and xi's into del of f naught xi's is equal to 0 for I equal to 1 to n. And now we come to equivalent convex problems. And first is eliminating equality constraints. Equality constraints is of the form of linear. It is linear, so uh, we can find a particular solution x naught of this and a matrix F which is in the whose range is the null space of A, and then we can rewrite the equation as the optimization problem as for some variable z plus x naught subject to the inequality constraint. So for I equal to 1 to m, and moreover this is also a convex optimization problem because uh, the affine function, the composition of a convex function with an affine function preserves convexity. And we can also see another epigraph problem. We rewrite the convex optimization problem in equivalence of epigraph problem, where we minimize t subject to f naught of x minus t lesser than equal to 0 if I of x is lesser than equal to 0 and the affine functions bi's. So we can see this is convex because t is linear and hence it is convex. F naught of x minus t is also convex in x comma t, and the rest are the same. So this is also a convex optimization problem. And now we briefly see quasi-convex optimization problems. Here we have to minimize f naught of x subject to the inequality constraints and equality constraints, and here the inequality constraints are convex and equalities are fine, but the objective function is quasi-convex. This leads to a immediate observation that the global optimal is not equal to local optimal. We can see this by the diagram. Here x is optimal in its vicinity, local optimal, and y is global optimal, and this is a quasi-convex function. And also we talk about quasi-convex optimization via convex feasibility problems. So we break the quasi-convex optimization problems into small chunks of convex feasibility problems. Uh, so our approach is representing the quasi convex functions via a set of sublevel sets of quasi convex functions via family of convex inequalities. Okay, so here the sublevel sets of quasi convex functions, sublevel sets of quasi convex function f, we choose this as convex such that is lesser than equal to f naught of x is lesser than equal to t is described by phi of phi t of x lesser than equal to 0, where phi t is a function from Rn to R and t belongs to R. It is a family of the convex functions. So phi t is lesser than equal to 0 means phi t is non-increasing function. Therefore, if phi s of t is lesser than equal to phi t of phi s of x is lesser than equal to phi t of x, this is for the condition s is greater than equal to t. Means okay, so we say p star is the optimal value of a quasi convex problem if the feasibility problem x, find x subject to that is phi t of x lesser than equal to 0, fi of x lesser than equal to 0 and ax equals to b. So if this feasibility problem is feasible, we can see that the optimal value will be lesser than equals to the value of t, and we can also see that this is a convex optimization problem. So if it is feasible, then p star is lesser than equal to t. So what we can see is that by solving this convex feasibility problems, we can solve the quasi-convex optimization problems, and this can be done by following a simple algorithm using bisection, solving a convex feasibility problem at each step. So we start with a interval, and in that interval we find we know that the optimal value p star exists, and we solve for the midpoint of that interval, and uh, we determine whether the optimal value is in the lower half or the upper half of that interval. Then we update the interval and solve for the new interval, and we repeat until the interval is small enough Next we see linear optimization problems. Here the objective and the constraint functions are all affine. So we need to minimize CT, C transpose X plus D subject to Gx, the inequality, and the equality X equal to B, and G belongs to cross M, and A belongs to we we call them, these kind of problems, as linear program, or in short LP. And we generally tend to say that we minimize C transpose X. This is similar to minimizing C transpose X plus D, which is kind of a shift by a constant. Also, maximizing C transpose X plus D is similar to minimizing minus C transpose X plus minus D, which is convex, and this is also called a linear program. To see the geometric interpretation, we find that we see that the feasible set of the linear program is like a polyhedron. So if we can draw so the sublevel, the level curves of the hyperplane are orthogonal to C, are like just like a dashed lines, because C transpose X is linear, and we say that here, let's suppose this is where it is the X transpose is the optimal point, and this closed figure is the polyhedron, the, the polyhedron that is the feasible set. It's kind of this is a kind of geometry. Standard form, linear program, we minimize, we just ignored that part, D part, and subject to equalities and component wise inequalities. So there is no other inequalities in the standard form, and then there is a specific another type of um, form of linear program, that is inequality form linear program. This does not have any equality constraints, so we minimize over C transpose X subject to AX lesser than B. Then we see converting linear programs to standard form. We do it similar to how we used to do it in optimization and convex optimization uh, problems by introducing slack variables. So the first step is to introduce the slack variables, and we try to bring it to the standard form, that is this. Only there will be only component wise um, inequalities, and equalities will be also there. So we minimize this subject to so we are bringing it from this is the form we have stated initially, so we are bringing it to the standard form. We are introducing the slack variable s such that gx plus s is equal to h, and then we write s is component wise greater than non-negative, and ax equals to b. Now one more step we have to perform, because we can see that this is still not in the standard form, because not all the component wise, like x is not in the component wise form, inequality form. So we have to uh, change we have to introduce two more variables. So we replace x by two non-negatives, x plus and x minus, such that their difference is x. Two non-negative variables, that is x plus is also component wise greater non-negative, and x minus is also non-negative, and this modifies our problem to C transpose X plus minus C transpose X minus plus D subject to Gx transpose Gx plus minus Gx minus plus the slack variables equals to H S component wise greater than equal to 0, X plus greater than equal to 0, X minus greater than equal to 0, and Ax. Let's okay let me write this first. So we can see this is indeed in the standard form now. Next we see one example of linear program. So the example is of diet plan, diet problem. So the problem goes like, uh, so there are m. So healthy diet. So the problem goes like, there is a healthy diet, and for having that healthy diet, uh, it requires m different nutrients to have a healthy diet in different quantities. So m nutrients are there. We require them in at least the quantities mentioned. The quantities are the BIs. For i's goes from 1 to m. So these are the at least the minimum quantity that you should have in your diet. Then so then there are different foods. There are n foods of different quantities. So the quantities is the solution set we are looking towards, the optimal value of x size such that I equals to 1 goes from 1 to n. These are the quantities of the n foods where these m nutrients are found, and we are trying to find the we will actually let me describe it first. Okay, so there are n foods and m nutrients, and then there is a matrix, the A matrix, where the ith column is for the nutrients, and the jth column is for the food. So a given food has a given nutrient in this amount, Aij. This is the amount of that nutrient found in this food. And then there is Cj, that is the cost of that food. So we have to minimize the cost such that we have all the m nutrients in at least the quantity BIs. So the problem, that is the problem statement, and we re replace it by a equivalent linear programming problem. So we need to minimize C transpose X subject to AX greater than B, greater than equal to B, and X is non-negative. Of course, the X, the amount, the quantities of food will be non-negative. Next, we discuss linear fractional programming. We need to minimize f naught of x subject to this. Looks similar um, to the linear program. However, the objective function here is a ratio of affine functions. And the domain of f naught is x such that E transpose x plus f is greater than 0. This is the objective function is f naught is quasi-convex, and quasi-concave. So we know that the linear optimization programs are convex optimization programs, and if the f naught, the objective function, is quasi-convex, then it is a quasi-convex optimization problem, which is in this case it is. So uh, our objective is transforming it into a linear program. We see that the feasible set is so our objective is to transform this into a linear program. So as follows. We want to convert it into such form. We can let me write this first. We can immediately see from here is that we have reduced this the ratio of some affine functions to just an affine function. We somehow changed the denominator by 1 such that we changed it from this to another function this, and the equivalence and this equivalence comes from choosing a particular y and a z, such that this is of this form and the z is of this form. Then we can see immediately that putting these values in this will lead us to the value equal to 1. And this indeed is uh, of the form of a linear program. And there is also generalized version of uh, this linear fractional programming, where the objective function is pointwise maximum of quasi-convex functions, of R quasi-convex functions, like in the same form. And pointwise maximum of quasi-convex functions is quasi-convex function when R is equal to 1, and this is the same linear fractional programming. Fractional programming. Thank you.